So today we are going to wrap up chapter 7. This is the third lecture on the topic of vector spaces, the first part of it. And what we're going to do, we're going to end the chapter with accomplishing our objectives. And that is, given a set of, in general, rectangular equations, rectangular matrix equations, we want to know the existence and uniqueness of solutions. So all the stories we talked about, it was to build up to this point that we can talk about that. And we are going to see a new factorization algorithm, LDLT. First, it might seem very somewhat new, and maybe you're going to say, oh, you have to learn another one. How many factorization are we going to learn? But then we're going to connect it to LU, so that should give you some comfort that it is actually not new. It's just a special case of LU. And that's good news. Now, to refresh your memory, you remember we reached a concise definition of linear independence. And that was, given a set of vectors, V1 to Vm, a linear combination of them was alpha 1 times V1 plus alpha 2 times V2, and so on. Then we set that to be equal to 0, and we said if solution to this system, we called it homogeneous system of equations, if the only solution was alpha equals 0, that was the trivial solution, and that implied the linear independence of the columns of A, and that was the pro tip. Otherwise, what was the consequence of that if there is a non-trivial solution to the homogeneous system of equations? We talked about it. We're going to formalize it today. But we repeated that a few times, what can happen. If you can recall, maybe tell me.
Linearly dependent, Professor.
Linearly independent, right. So if alpha 0 is the only solution, right? The columns of A are linearly independent. And if it's not, then the solution, right, was not unique, because there could be an alpha that when we multiply it by A gives us 0, and we could add that to any other solution, and that would not change the equation AX equals B. So that was a concern, and we wanted to understand when we have to deal with these cases, because then it's concerning. The solution is not unique, and we want to be aware of it. So to recap, the pro tip was telling us if you have A times alpha equals 0, this can be a rectangular system. If you multiply it from left by A transpose, you can always convert it to a square system of equations. And that was great, because then we could talk about the determinant. And then we showed that logically this is the same as the first case, because it didn't change the solution. They were equivalent. And that was important, because otherwise you could change the solution of the first problem. We don't want that. So these two are equivalent, because we are not changing the solutions. And we're going to see more of this A transpose A today. This is a very special term in linear algebra. You see that a lot. Okay, so pro tip was saying that consider a set of vectors in Rn. These vectors are n-dimensional vectors. And we have m of them, right? So m vectors, they belong to Rn. So each of them is an n by 1 vector. We stack them into a matrix to form an n by m matrix. So you're given these vectors, and we stack them, we form this matrix A by just saying V1, V2, Vm. Okay? And that will give us an n by m matrix. Then we have these equivalency of facts that the set of vectors are linearly independent. It's the same as saying the m by m matrix A transpose A is invertible, which is the same thing as the determinant of A transpose A is not 0. Or we can say, if you perform the LU factorization, possibly with permutation, of A transpose A, there is no 0 on the diagonal of U, because we know on the diagonal of L, we had only ones, right? So we had A, we had LU, right? L was lower triangular, but we would normalize L each time we were performing our LU factorization, so that we get ones on the diagonal. If you don't remember this, if you go back a few lectures, when we were going through that painful process of find a pivot, form the multiplication, subtract it, right? All of that. And then it led to an algorithm that could do it for us. But U is basically upper triangular with no constraint on the diagonal. It could be any number. Now, we're saying that there is no 0, right? If you see a 0, we know that the determinant will be 0, right? It violates that condition. We know that it won't be invertible. And that will lead to the set of vectors not being linearly independent. And as a rule, you can test that if 2 columns of the matrix or 2 rows are a factor of each other, the determinant will be always 0. That's like an obvious linear dependence. It's a very trivial case of it because we can detect it with eyes. You see that the first column is twice of the second column, then you know that already. That's the case. Now we're talking about large matrices. We cannot recognize it by eyes. We want to calculate it numerically, right? So that's why we are building it systematically like this. So one example to, again, refresh your memory. Determine if the set of vectors V1, V2, V3 are linearly independent. Tell me, what should we do? This is a question. You might see it in homework and other problems. Where do we start? Setting up an equation A, B. But we don't have any B at this point. I am just giving you V1, V2, and V3. I want to know if they are linearly independent, right?
Yes, if you set up an equation like we find the coefficients, A times U1.
Okay, you're saying we formed a matrix? Or you're talking about the definition, right?
Yeah.
Okay. That's right. So one way was, well, the definition is telling us that we have some coefficients times a vector equals 0. And we can always rearrange this into the matrix equation. And in fact, A is V1, V2, and V3 in this example. So this is the definition, that's where we start. So whenever you see this question, this is the starting point. What's after this? Okay, we use the definition, we wrote that, we know this is what we want. What's next?
We find the determinant of A.
But A is not, okay, the one idea is that let's find the determinant of A, but A is a rectangular matrix. That's a good idea, but rectangular matrices, they don't have determinant. We cannot take the determinant of A, it's not defined. We should solve A times alpha. We should. How? No, we can solve, so there are two things. One thing is, what is the value of the alpha, right? And the other thing is, the question is asking if they are independent or not. So you could solve for alpha and show that that's the case, but you could just verify whether they are independent or not without finding the alpha value. So that's okay in this question. Okay, one idea in chat. Multiply A by A transpose. That's a good idea. From right or left? Whenever you say multiply matrices, you need to mention from left or right. Ben, left, okay. So can we do this? Can we say A transpose A alpha equals 0?
Instead of doing that, can't we just find the determinant of A transpose alpha? If it's not 0, then
Yeah. Can we, you're saying that can we find the determinant of A transpose A and just conclude that they are independent or not? And that's exactly the solution, because I'm going to go back, refer to the pro tip, right? Any of these items that you do implies independence or dependence. So if one is satisfied, that means all of them are satisfied, they're equivalent. If one of them is violated, that means all of them are violated. That's the meaning of the following or equivalent, that precisely that's what we mean. Now you might find one of them easier in different cases to do. Of course, the easiest case here, if we have access to Julia to calculate the determinant, right? Just take A transpose A, determinant of that, and that should tell you the answer. Okay, so the determinant idea was good, but we can't do it for rectangular. We say that the determinant of A transpose A should not be 0 if we want the vectors to be independent, right? And let's see what we get. So we formed a matrix A. That was our first step. It is 4 by 3. We check that the determinant is 100. You're going to hate me. I manipulated this matrix to get a really nice number for the determinant, 100. All of your homeworks are very complicated numbers. And you enter one less floating point number, and then other grader complains. It doesn't happen on slides. Okay, so the determinant is 100. Would it make any difference if it was 91? No. What about -1? No, it doesn't matter, as long as it's not 0, right? That's the conclusion. That's the pro tip. Convert A times X to A transpose times A, X, or alpha, equals 0. Take the determinant of A transpose A. If it's not 0, the vectors are independent, linearly independent. Okay, so hopefully this sets your mind back on track. This is where we ended last time. And I'm going to build on this. We will see another example, and we're going to get stuck in somewhere. That will help us to realize what's actually missing. And remember, we want to know existence and uniqueness, okay, of the solutions of the system. Now, this is a good knowledge to have. We're going to see this matrix again and again. In the previous chapter, in the book, there is a part on symmetric matrices. If you didn't read it, I'm covering it here. Now, what happens when you calculate A transpose A? In this particular case, when we look at it, what do you see here? What is special about this matrix? I'm calling it symmetry. What do I mean by symmetry in this matrix? So your idea of symmetry is that that matrix, which is A transpose times A, if I take its transpose, I get the same matrix. Now remember, A times B transpose was B transpose A. Now, A transpose times A, and we also know that A transpose, if you swap, rearrange rows into columns and do it again, then you get the same matrix back. So what happens is that A transpose A, which is true for any matrix just multiply it from left by A, this is giving you a square symmetric matrix. Now, whenever you have this condition, right, or you can say if A transpose equals A, take any matrix, calculate this transpose. If you get the same matrix back, you call that matrix symmetric. And that means, imagine this is the diagonal. Whatever is in both sides is the mirror version of each other. So I have these guys here, 1 and 1, -3 and -3, right? In other words, the entry A, let's call it A, or just 2, 1, is the same as 1, 2, right? Now, this is clearly a very special matrix. It is a square, it is symmetric. Now, A transpose A always gives us this. So these matrices are very special, and they're called symmetric. Now, this is even more special than that, but we're going to talk about it in the future. Although we see some of it today, but I'm not going to talk about positive definiteness, but this matrix has that property too. So a matrix is symmetric if its transpose is equals to itself. That was just a fun fact. We get back to it later when we talk about LDLT. Existence and uniqueness of solutions to AX equals B. The following statements are equivalent. We're going to say the system of linear equations, AX equals B, has a solution, and it is unique. It's the same as saying B is a linear combination of the columns of A, and the columns of A are linearly independent. Okay? B being a linear combination of the columns of A, we talked about it last time, that means that it's the weighted sum of the columns of A. We can reproduce B by weighting each column of A with an arbitrary weight and then sum them up. That should reproduce B. If you can't do that, then what does it mean? What does it mean if I can weight each column of A, sum them up, and get another vector, call it B? That means, well, this equality is satisfied, right? The equation, the set of equations is consistent. The right-hand side and left-hand side actually agree with each other, because otherwise there cannot be any number if the equality does not hold, right? Okay.
So is this process of checking for linear independence just a way to check whether a system of linear equations is a rectangular matrix?
Yes. The question is, are we doing all of this, linear independence, to know that a system of rectangular system of equations, first of all, has a solution, and if it has a solution, if that solution is unique. Because if it's not unique, then there are infinity of solutions, right? There's only one unique solution or an infinity of solutions, or there is no solution. Very first lecture we talked about it with lines and all of that, right? This is like a very advanced version of that, any dimension, any size. So it sounds like we have two jobs to do. First, we need to make sure B is a linear combination of the columns of A, and then we have to make sure the columns of A are linearly independent. We just did that, right, in the previous example. We know how to do the second one. So that's just a remark for what we talked about. If B is a linear, you can express it as a linear combination of the columns of A, that just means that the system of equation is consistent. It makes sense to have that equality sign. And there is a solution. But although it might not be unique, for uniqueness, we need to look at the columns of linear independence among columns of A. Which I'm repeating again and again, because if the columns of A are not linearly independent, then there is a non-trivial solution. That means alpha not 0, right? Such that we can have A times alpha equal to 0. Then if there is a solution, such as x bar, then A times x bar plus alpha is also a solution. So there are an infinite number of solutions, and that's the problem. Because, again, there are an infinite number of solutions. You might say that, well, there are two solutions, right? You just have one alpha. But notice that I can multiply this alpha with, let's say, constant c, just a scalar, right? from the rules of scalar times vectors and matrices, we know that C times alpha equals 0. C will come out, right? And if that alpha satisfies this equation, so does C times alpha. And C can be anything. You can scale alpha anywhere you want. It works, okay? So a deeper discussion on this is in chapter 9, related to the null space of matrices.
If C times alpha could also be a solution, does that mean that there's an infinite number of solutions regardless of what alpha is?
That means there is an infinite number of solutions regardless of what C is, not regardless of what alpha is, right? Because alpha is that direction that satisfies this homogeneous system of equation, right? But C can be an arbitrary real number, whatever it is. It's not going to affect the fact that I can add it to the solution, right? Because that term ends up being 0. I don't even notice that in that equation that I have here, okay? That's the reason we have infinite number of solutions. Because it's not just one of them. The moment you have one of them, you can multiply it by many real numbers, and there are infinite number of them, okay? Now, this is an abstract version of that. It's not like we were drawing a line and talking about now lines are parallel or intersecting, right? We can't do that here. We need to resort to more abstract concept. Okay. There's a heated discussion in chat. Should we? Ben is confused. That's a good question. That if you have AX equals B and find that the columns of A are linearly independent, can you conclude that there is one unique solution? Can we? That's literally one side of the story. There is the other side of the story, and that's B, right? So the columns of A being linearly independent, that's just one side of the equation. And that means there is a solution. To be unique, then we need to look at B, because it's important what's the value of the right-hand side. Okay? So if the equations are consistent, that means B is a linear combination of the columns of A, and also the columns of A are linearly independent, then we can claim that there is a solution and it's unique. So we need to look at both sides of the equation, not just one side. And again, as usual, we're going to have a method for doing that. This is all over the place. We need something that systematically say, okay, first do this, second that, and then that should give us a conclusion. That's what we're working on today. Example. Does the following rectangular system of equations have a solution? If it does, is it unique? What should we do? Tell me in a starting point. I need a starting point. Right. What about first, let's check the columns of A, right? We know how to do it. That's like the previous example. So the uniqueness comes from, this is the uniqueness test. we check that the determinant of A transpose A is the same matrix as before, as the previous example. We check that the determinant of A transpose A equals 100. Now that's not 0. Then that passes the uniqueness test. Okay? What about the existential problem? Now that only tells us that A is not a deficient matrix. It's not. There's nothing wrong with the left-hand side. The columns of A are linearly independent. That's all good. But given a right-hand side B, we do not know that yet there is a solution. That's the same thing as saying, I want to check to see if the system of linear equations is consistent or not. Here's a trick. B is just another vector, right? How about we add B to the set of vector that we had from, this shouldn't be, this actually should be like this. Because vector had order, right? When I write it as a set, then there's no order. It's okay, but if you want to really be careful, it shouldn't be like that. So the idea is that I check to see if V1, V2, and V3 and B are linearly independent. And what do we want to see?
If the transpose of that times itself, the determinant of that, whether it's equal to 0.
Yeah, you're explaining the steps, but very high level, right? What we want to see if B is a linear combination of these vectors, right? Now, what does it imply? Do I want to see the determinant of, right, this new A transpose time A is 0 or non-zero? Not 0.
Yes.
Not 0. So you're saying, let us form A transpose A and make sure this is not 0 to conclude that there is a solution. Okay. I appreciate the effort, but we're going to do exactly the opposite. Well, because if it's non-zero, that means they're linearly independent. That's what we just did for A, right? Yes, we want it to be linearly dependent because we want to weight each columns of A to produce B. So unlike the first test, the uniqueness test, that we want the determinant of A transpose A to be non-zero, for the existence test, to check that there is a solution or not, then B should be a linear combinations of the columns of A. That means that if you add it to the set of vectors that are columns of A, it should not basically be independent of them, right? B is not independent of the columns of A. That's what we want to see. All right, so we form a new matrix A, call it A subscript E. It's the same notation we have in the book. You can call this an augmented matrix or system. Now, if B is a linear combination of the columns of A, then these two set of vectors, this one, V1, V2, and V3, and also the same set with the addition of B, they must have the same number of linearly independent vectors. which is 3 here, columns of A. And how do we know how many they have? Based on everything I talked about today, how can we tell that how many number of linearly independent vectors we have in each set? Can you repeat?
Number of B's in your A.
Number of B vectors. Here, B is just one vector, one column.
Yes, so if you have 3 columns in both of those, they're all B. No, sorry.
Because our B's all just column vectors.
Now, I want to know, I have these 2 sets, and I want to know how many number of linearly independent vectors I have in each set. Of course, if I have 3 vectors, at most I can have 3. If I have 4 vectors, at most 4. But I want to get a number per set and then compare them. And they must be equal because B should not add an independent direction to this set. If it does, it's not a linear combination of the columns of A. Now, how can we tell they have the same number of linearly independent vectors? And to say that we need a way of knowing how many, right? So that was a trick question. We do not know how. We're stuck here. We do not have a way of telling how many vectors or what's the maximum number of vectors in a set of vectors are linearly independent, right? Sounds like we need something extra here. We're not able to solve this yet. Does it make sense why? We need to know the number of linearly independent vectors in a set. So we can count it. And then we can check whether these 2 sets have the same number of linearly independent vectors. Because if you're saying why do we need to do that? V1, V2, and V3. These are the columns of A, right? And we said we want them to be independent. And I also B to B alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3. So now, if I create A out of this and A, E, do I want how many number of linearly independent vector I want here, given that I need B to satisfy this property to keep the equations consistent? Three? Yeah, the same as A, right? Because you can just substitute B based on this weighted sum of the other 3 vectors. B, by construction, is dependent on those. So you should not add an independent column. Now, of course, we're given a B in practice, right? But we want to check if that's done correctly or not. And if it's not, we know that something is off with that system of equation. That means there is no solution.
Sorry. Does this logic also hold for checking, like, if B is independent of B1, B2, B3, then there is no solution? Like, does this logic of BD construction of B1, B2, B3 also serve as an explanation for that?
Yes, so there will be, you're saying that if the logic will tell us if there is a solution or not, right? Yes, because this will be a way to check if the equations are consistent. And if you remember, first day, what we said, if they're not consistent, then there is no solution. And that was one of the three cases. We had three cases. There is no solution. There is a solution and it is unique. There is a solution and it is not unique. That means there's infinity of solutions. And this will help us to answer that question. So we need something extra. By attempting to solve this problem, we reach to a new problem that we need a way to know the number of linearly independent vectors in a set, not just knowing that they are independent or not, but also knowing which of them are independent and how many of them, right? That will give us much more information about that set. Okay, so that's basically the question, and we talked about the importance of it. And the importance of it comes from the same problem. We want to solve a system of equations. It can be rectangular. We need to know if there's a solution or not. Okay? And if it's unique, if there's a solution. And the fact that B is linear combinations of the columns of A. And that tells us B is not linearly independent of the columns of A. So that's two independent tests, but completely different expectation, right? The first one, the expectation was that to be independent. The second one, we expected not to be independent so that we get the same number of linearly independent vectors, and that means the system of equation is consistent. That's the whole story here. And to formalize the problem, given a system of equation, right? Ax equals b. What I want to do is that make a set out of columns of A, also make another set, and add B to that set. Okay? Then I want to check if they have the same number of linearly independent vectors or not. And we call this the Uber pro tip. Previously we had a pro tip. This is our Uber pro tip. We're going to come up with an enhanced LU factorization method. Same as previously, consider a set of vectors, v1, v2, vm. They're part of our n. We can stack them into a matrix, form matrix A. A is n by m. Now, it is a fact that any matrix of the form of A transpose times A has an LDLT factorization. LDLT because you can factorize a matrix by LDL transpose. And that transpose accounts for this T here, right? This is LDL, but it's L transpose, the second one. We call it LT. Okay, so LDLT means L times L, D times L transpose. Now, what are these terms? Because it's got really complicated. This guy here. This is the same as the previous cases. This is the permutation matrix. We'll permute the rows of our matrix A, okay? It's performing row exchange for us. What about the other one? We have two. Now we have P transpose here. what does it mean to multiply a matrix by a permutation matrix from right? Now, you might guess that will exchange columns, right? We didn't talk about it because LU with row permutation gave us everything we needed. There was really no need to talk about it. But when you multiply a permutation matrix, you can try it. Just test it using some examples. Same idea as before. Instead of rows, we can exchange columns. And that's what really is doing. But it is not any permutation matrix. It is the transpose of P, okay? L is uni-lower triangular. What does it mean, uni? Uni is unit triangular. And then we call this, you can put dash as well. And what we mean the diagonal of that triangular matrix has only ones, right? For example, 1, 0, 2, 1, 3, 1, 0, 0, 0. Maybe this is a unit triangular matrix. To be more specific, it's a unit lower triangular matrix. Make it a little shorter, it's a uni lower triangular matrix, right? Yeah, go ahead.
So for unit triangular matrix, everything under, it doesn't matter what's underneath the diagonal?
No.
The diagonal is all
Yeah.
ones, and above the triangle is going to be zeros.
Yeah, so it is still a lower triangular matrix. It's just the diagonals are all ones. And you could have the same thing. You can have a uni upper triangular matrix. Same idea, okay? So it's a special case of triangular matrices. So L is unitriangular, and it's a uni-lower triangular. And obviously, L transpose is just the opposite of it. It's a uni-upper triangular matrix. I'm just introducing these new matrices to you. They're new friends. Should have people dress as LDLT here with costumes. Last one, D, is a diagonal matrix, and it's non-negative. Now, this is, again, it's a good topic to revisit when we talk about eigenvalues. We don't want to talk about it now. When you have this type of A transpose A, for the same reason that x squared, it's always non-negative, right? It can't be 0 or any other positive numbers. For a generalized version of that, for matrices, D is a diagonal matrix. It can have 0 or any positive numbers, not negative, right? That's just a quick reason why it's like that. We can revisit this later when we talk about eigenvalues. So D is a diagonal and non-negative. Entries are non-negative. Okay, all of that is giving us this LDLT. Now why, I'm going back here to why do you think we have column permutation? Previously we had only row. But also, is this a new form, or how far we are from LU? Because previously it was much simpler. It was P times A would give us LU, and that was it. Now, we could talk about P times A transpose A LU, right? That's also okay. Now, you might guess that if you define you can define U to be D times L transpose. This is going to be just an upper triangular matrix, right? You get the LU back. This is not different than the previous LU factorization. So that should answer your question that this is in fact LU. It's just a more special case of LU. Now, for the reason we can factorize it into U being a diagonal matrix times L transpose, and L is actually the same L we have here, this forms some sort of symmetry here because both L and U are made of the same matrix plus a diagonal matrix in the middle, okay? Is this interesting to you? See, you're very excited to see L transpose. Now, the reason is that to have this beautiful formula that you get L and then L transpose, it's very convenient. We talked about it that A transpose A is symmetric, right? Now, to keep everything symmetric, we needed that P transpose on the right. Otherwise, right, it wouldn't work because when I write this and I transpose it, I get P, A transpose, A, P. Now, A, B, C, D transpose, same idea as A, B transpose. It's D transpose, C transpose, B transpose, A transpose. So what's going on is that transpose, right? By performing both row and column permutation in the algorithms, we're trying to maintain the symmetry also in the factorized version of A transpose A, because A transpose A itself is symmetric, right? Now we're doing some extra work. It's actually less work, but what you see is extra work to maintain the symmetry of the problem also in the factorization, and then you get this beautiful formula of L, D, L transpose. Because previously L and U could be totally different, not related. Now U is somewhat related to L. And that's due to the symmetry of A transpose A. Now this is the reason, the motivation for having this type of permutation matrices that you see here. Now, why are we looking into this more special case of LU than LU itself? Because this is the right tool for telling us how many vectors are linearly independent, right? This is the factorization that can tell us without any caveats and any special cases that you might have to deal with. This is the fact that this is the right tool for this problem. So the number of linearly independent columns of A is equal to the number of non-zero entries on the diagonal of D. So we can count it now. We perform the factorization. You're going to use Julia. You're not going to do it by hand. Although there will be an algorithm in the lab, we can talk about it. And it's a good challenge to implement the algorithm in the book. but ultimately you want to use a library. We perform LDLT, you look at the diagonal of D, which is a vector, right? You can put the diagonal of a matrix in a vector. Then you count the number of non-zeros, and that's the maximum number of linearly independent vectors in a set. Okay, so again, to reiterate, I can see a question in chat too. LDLT factorization, also called Cholesky factorization, it can be seen as a special case of LU when U is D times L transpose, which is not true in general, right? Just for symmetric, positive definite matrices. Matrices of the form of A transpose times A. So that's the relationship between LU and LDLT. Cholesky was the name of the mathematician, French mathematician who looked into this problem, had the early version of the algorithm. It's actually LL transpose. And then there's LDL transpose, right? You can have different versions, and you can convert between these two. LDLT is nicer because you actually separate. This L is unitriangular, and D will just give you these numbers, and you can look at it to see which one is non-zero. Otherwise, it's all mixed up here in LL transpose. Now, I added a remark, so you revisit this idea that Y, this is symmetric. So P times A transpose times A times P transpose is a symmetric version of A transpose A with permutation. And you already know we need permutation in factorization to deal with the cases when the pivot becomes 0, right? So the solution to the case when the pivot was 0 was to introduce permutation, exchanging rows or columns. So this is a general version of that. Okay, to clear everything, suppose I have a uni-lower triangular matrix L, right? What is L transpose? Tell me, I write it. What about the second column? 2, 1. So just take each row and put it in a column, right? So what did you see? Well, L transpose is upper triangular. So the transpose of a lower triangular matrix is always upper triangular, and vice versa. Okay? That's why D times L transpose is upper triangular. And D is a diagonal. When you multiply diagonal matrix, it's not going to change anything in the structure of L. So without P transpose on the right, this term, the whole thing on the left, won't be symmetric. And that's the reason we're doing it. Now, I'm going to claim that obviously if I am saying the left-hand side is symmetric, the right-hand side must be symmetric too, right? You can't have one side symmetric, there's equality, and then the right-hand side is not. So you can check that L transpose right? And the diagonal matrix, when you transpose it, you get the same matrix back because it has only diagonal values and zeros everywhere else. So you get L transpose. So by maintaining the symmetry during factorization, our factorization is also symmetric. You transpose it, it doesn't change anything. Why this is good? A lot of times it's useful when you do maybe derivations and then the symmetries helps you to simplify something. Why it's useful computationally? Well, symmetry in math is an important topic, and it happens a lot of places. We have it also in nature too. Now, because of that symmetry, we can save a lot of computations. And in fact, Cholesky factorization, or LDLT, is twice as fast as LU. If you're working on a problem and your concern is only speed, LDLT is, if applicable, right? Because it's more special, you need to have A transpose A style. Then it's twice as fast as LU. So in fact, we use two types of factorization in famous libraries, for example, for robotic mapping and solving a SLAM. One is Cholesky, the other one is QR that we will see in chapter 9. Cholesky is faster, but numerically less stable. QR is slower, but numerically stable, the versions that we have in the libraries. So there's this trade-off of speeding things up, but you might face some singularities too. Okay, so but this is not a coincidence that it is faster. It's not by chance at all. So whenever you have symmetry, that means you can save doing extra calculations for things that are similar, right? For things that are similar, we do not repeat the calculations, and that's the consequence of having symmetry in a problem. Okay? Now this, imagine that I have A transpose A to be L110, L21, L22. Right? How many numbers do I need to know? Now the total number of free values here are 4 plus 4, 8, right? My matrix is triangular. I have 3 plus 3, that's LU, right? 6. Cholesky, 3. Because the upper triangular part is the same as the lower triangular part. It's just I can save on recalculating, right, some of the elements. But try multiply it and then put both sides equal to each other. That's, in fact, how you can derive a formula for 2 by 2 or 3 by 3 Cholesky factorization. But we don't have to do it for this course, but in some linear algebra courses, when they dive into the actual Cholesky algorithm, they use this as examples. And here is a challenge for you. Now, to really understand what's going on, why it's faster, write a Julia program, take a notebook, right? Generate symmetric matrices like A transpose A. For example, you can generate the matrix randomly by some size, right? And then calculate A transpose A. That will give you a symmetric matrix type that can be used for Cholesky factorization. Then compute LU and LDLT and time them. Use TikTok to calculate the elapsed time and record them. And then grow the size of the matrix. Maybe first your A transpose A is 10 by 10. First it's 1 by 1, 10 by 10, 100 by 100, 1,000 by 1,000, 10,000 by 10,000, 100,000 by 100,000, right? See how far you can go, as far as your computer allows you to do it. At some point, you have to just wait too long. You're going to give up, okay? Which will give you an idea about cubic time complexity. Now, create a table. Make a table, LU, LD, LT. And this is the, basically, the rows are observations for maybe, one is obviously non-trivial, 10, 100, 1,000, so on. You can make it more points, 10, 50, 100, 150. And these are time, right? T, right? Similarly. Now you have a table. Now go to, you can do it in Julia, right? Use this to plot. Now when you visualize time and matrix size, right? Like maybe it's log scale. What do you expect to see? Maybe you get something like this, right? Which one do you think is LU? Which one is LDLT? It's time. The vertical axis is time. So hopefully this is the curve you will get, and this is LU, this is maybe LDLT, right? Up to a similar pattern, but one of them you see is faster because it takes less time. In fact, you are generating the empirical time complexity of your algorithm by timing it for different input sizes. It's a good practice to do. And I'm going to claim that LDLT will be roughly, or even more than twice as fast as LU. Okay? This will be a fun practice to play around with these algorithms. Now, once you have this table, in fact, in the next lecture, chapter, we'll teach you how to fit a curve to these points. You have a bunch of points. You want to find the equation that goes through these points. That's the topic of regression. We're not going to be able to have a curve. We will only have points, right? We need to come up with a way to do this curve fitting. And that's the topic of regression. All right, this is a cool project. If you like to do something on the side, let us know if you do it. I think it will be fun to include it in the course as well. Example. Consider this system of rectangular matrices. The A matrix is 7 by 5. Pretty large enough. You don't want to do it by hand. B is 7 by 1. 2 questions. Does it have a solution? If it does, is it unique with everything we learned so far? It doesn't have a solution? How do you know? I'm very impressed. So,
from my intuition of just like, we're doing A equals B, then the number of B values needs to equal the number of X values. But for our A columns, we only have 5 columns, so we have 2 X values that wouldn't be matching. So if it's 7 by 5, or if it's not n by n, I don't think it's going to match. So it's not, doesn't have a solution.
so you're saying because A is not a square, it doesn't have a solution.
Yes.
And that's not correct because we can convert this into square system, A transpose A. Now, you are probably thinking a little ahead of where we are, where the number of columns were bigger than number of rows, right? What if this was 5 by 7? But in any case, for today's topic, we don't know by just looking at this right now. I am terrified now that you can look at it and draw that conclusion. You have a master computer in your brain. You can look at these numbers and calculate linear independence. Let's see, right? Let's check if it's true or not. Now, the first part was that A transpose times A. We need to calculate A transpose A, and we do it in Julia. Then we calculate LDLT factorization that we're going to give you examples in the lab. At least some examples you can be comfortable calculating it. And then we report what do we get from D. D is a diagonal matrix. If you take a diagonal as a vector, we look at the numbers. Now the numbers are all good except this one. You get 1, 0. And our conclusion is that there is a single 0 on the diagonal and 4 non-zero elements. Then we know that exactly 4 out of 5 columns of A are linearly independent. That was our uber pro tip, right? This comes out of uber pro tip. Now that's a problem because to have a unique solution, the columns of A must be all linearly independent. So if there will be a solution, that solution won't be unique. That's our conclusion here, okay? So if there was no 0, we would conclude that if there will be a solution, the solution will be unique, the opposite of this, okay? So this was the test for uniqueness of the solution. Now we're going to test for the existence of a solution. Our uber pro tip was saying that form this augmented A. The question is D diagonal of, D is diagonal of this D. So D is a diagonal matrix like this.
How do you get that?
Julia. I did not calculate it by hand. Yeah, we're going to use the software to do it. I mean, you're welcome to do it by hand. We had some examples how to do it. And there's an algorithm, but that's tangential to the point we're making here, right? So assuming we have a way of getting LDLT, I use Julia to do it. I can run this test to know if the solution is unique. It wasn't unique because I had a 0 here. Now I want to see if there exists a solution for this problem. Now what I'm going to do what we couldn't do last time, I'm going to augment A with B to calculate A subscript E. Then I'm going to factorize A transpose A, A subscript E transpose times A subscript E. That will give us a new D matrix, right? Instead of 1 by 5, the diagonal will be 1 by 6. Now, what happens is that I get 2 zeros. And what does it mean? Adding B as an extra column to A resulted in 1 extra 0 in the diagonal. B is dependent, right? So that conclusion is that B is dependent on the columns of A. It's not linearly independent. So the opposite would be that now suddenly we still have 1 0. Adding B adds a non-zero. That's the sign that equations are not consistent. Okay, so we note that there's still 4 non-zeros. Our conclusion is that B is a linear combination of the columns of A, okay? Hence, our system of linear equations has a solution, right? Has a solution. It is not unique. What does it mean? There are an infinite number of solutions. Exactly. So uniqueness and existence, 2 different parts, right? So that's the takeaway. And this LDLT and augmented version of that when we add B gives us 2 different tests, and we check that. That's the whole message of today in this chapter. So we have a way of knowing uniqueness and existence for any system of linear equations now. Day 1, we had no idea what to do. As of today, any system I give you, you can tell me if there is a solution, if it's unique or not. Okay? Now let's try another B, right? Just make it, okay, go ahead.
For the other slide, if the last term of the diagonal was any positive value, would that mean that there are no solutions?
If the diagonal are positive or?
Yeah, if the last term of this diagonal.
Oh, that's the next case, right? So let's just entertain this idea of the opposite case, right? Let's say if we were given another B. B would be this B tilde. Run. So form a new, right? A. This is A. And then calculate LDLT. Take the diagonal of the new D. Now this time, you see that the result is still 1 0, and adding that B resulted in, now these are somewhat sorted. It's not exactly sorted. But resulted in still 1 non-zero. So adding B added 1 non-zero to D, right? Adding B here added a non-zero term to D. So what's the conclusion now? Exactly. So this is the opposite of it, right? So the system of equation with this new right-hand side, B tilde, does not have a solution because B is in fact not a linear combination of the columns of A, and it's just an independent vector. And that means two sides of the equations are not consistent.
So, if the last term is 0, does that mean that B is dependent upon the first 5 columns?
Okay, this is for today. I'm not sure if after this it will be recorded, but I'm going to answer the question now, okay? So next time we'll talk about chapter 8, and we're going to talk about least squares and regression. That's a very exciting topic. So the question is, if